So good afternoon, everyone. It's kind of weird to say because I'm used to teaching in the morning, but I am down for this. Today we're going to be talking about section 1.1. So last time we kind of did some preliminary stuff. Today we're going to move into the actual content for the class. So I think the first chapter is all about functions. So we're going to learn about what is a function, what is the input versus the output, and then we're going to learn about some various types of functions like linear functions, okay, whose graph is a line, or we might learn about quadratic functions or polynomials or exponential functions. Some of those you might have heard of already, but don't worry, we're going to introduce them one by one. The first thing that I usually do at the start of every class is I just remind you about homeworks, assessments, and my office hours and the MTC. So next homework is going to be due on 1/16. I think that's Monday at midnight. So I always make my homework assignments due at midnight. I also give unlimited attempts on the homework problems, and I can't remember if it's Wiley or the other one that doesn't work well with that. So just keep an eye on it. If it's not giving you unlimited attempts, then send me an email and I'll try to get it fixed. Because I think it is Wiley, that it's a huge pain to figure out how to make it work. But you should have unlimited attempts on the homework problems. So you can try them on your own. You can then consult the textbook, try it again. You can go to office hours and get help during office hours, or you can go to the SI sessions with Jacob. So Jacob, do you have anything to say about the SI sessions?
No, I won't find out till tomorrow what time and where it will be, but I'll let y'all know. I sent out an email with the group meeting link. I'll send it in there.
Okay, so check the Blackboard announcements section or your email for the correspondence from Jacob regarding SI sessions. So SI sessions with somebody who took the class before, got a good grade, is now an SI. You can go to them in like the evenings, typically is when the SI sessions are, and you can get help for your homework there as well. So my goal for all of you is, look, your homework has unlimited attempts. You can get all sorts of crazy outside help, including from me. If you come to my office hours, we will literally sit there and do your homework together. And it'll probably be a lot easier than doing it on your own. So please come to office hours, make use of that. With all of the resources that are available, I think it's totally attainable to get 100% on the homework, like average, over the course of the semester, especially with 2 drops. So get as many points from the homework as you can, and you will not have to perform as well on exams. So that's better. Okay, speaking of exams, your next assessment, so assessment is quiz or test, is going to be quiz 1 on Thursday of next week. Content TBD, probably like 1.1 and 1.2. So the assessment questions will come directly from the homework. Office hours. So my office hours are going to be 11:30 to 1 p.m. Tuesday, Thursday in LeConte 439. That's the 4th floor of the LeConte building. Sometimes if I have a lot of people, I'll move, but if I move, I always put a note on my door and I send an email to the class saying, hey, we moved classrooms because there's too many people to fit in my office. So that's office hours. And then if you can't go to my office hours, the next best thing is the Math Tutoring Center, which you can go there from 10 a.m. to 4 p.m. Monday through Thursday. I think they close 2 hours early on Friday, and that's in LeConte 102. So you can go meet with another grad student. So between me, the SI, and the Math Tutoring Center, you can get like virtually 24/7 free, excellent quality math help for this course. I recommend that you take advantage of that early as opposed to after you've already sort of fallen behind. So just keep on top of things. It'll just make your life so much less stressful through the semester. All right, so are there any... Oh, one other thing. The syllabus. There's something wrong with the schedule. Somehow I messed up the date of the spring break. So the spring break was wrong. I'm fixing it. It'll be up soon. I'm fixing it. I think I put the spring break as like the week after the actual spring break. So you just take those 2 weeks and swap them. So that's about the syllabus. So any administrative questions before we start in on content for today? Yeah.
And you said we could schedule an appointment with you. It's not this one.
That's true. If you want to meet with me, but you can't go to those office hours, send me an email, and I'll send something back like, please tell me your availability over the next couple days for a virtual appointment or an in-person appointment, and then we'll work something out between our schedules where I can come into my office for like an hour or two or something like that, or we can meet online. And if we do an online meeting, basically what you'll do is you'll open up your computer and get onto like Microsoft Teams or Blackboard or something. You'll see basically my iPad screen and you'll hear my voice, and I'll be able to hear your voice and see you if you put your face on the screen if you want to do that. So that's how that would work. Does that answer your question? So yeah, you can schedule an appointment. Any other questions? Yeah.
Are quizzes in class?
Yeah, quizzes are in the last 15 minutes of class on Thursdays. Any other questions? Yep. Yeah, the quiz questions are pulled directly from the homework assessments. I'll modify the numbers a little bit to make them work nicely. Any other questions?
Did you say we would or wouldn't use calculators?
No calculators. So that's why I'm going to fix the numbers to work out nicely. You won't have to do anything crazy in terms of multiplication and stuff like that. More questions or? All right, cool. Then what we're going to do today is hopefully a lot less of me talking and a lot more of you doing math. But first I want to remind you of what we talked about last time and just kind of introduce the material for today. So last time we talked about PEMDAS, we talked about adding fractions and multiplying fractions, and we talked about preliminary set theory, okay? So we talked about what are sets. They're basically buckets. Our buckets contain certain things or they don't contain certain things. We can combine buckets by pouring them into a new bucket, or we can take the stuff that's just common between the two sets, okay? So those two operations were called set union and set intersection. And then we talked about special kinds of sets called intervals, okay, which are a collection of a range of numbers which are all larger than one number and smaller than another, okay? And whether we include or don't include the endpoints was a question of whether the interval was open or closed. So if it's closed, we use a bracket and we use a closed dot on the number line, and that means include, okay? If it's open, we use a round parentheses and an open dot on the number line to talk about these, to talk about not including the endpoints of an interval. Then we talked about functions. And the main thing that we need to know about functions is that for each input, there's only one output, okay? It's not a big deal if there's multiple inputs having the same output, but if there's one input having multiple outputs, then we're hosed, okay? And the way that you can visualize that in terms of the graph of the function is with the vertical line test, okay? So this was the last thing we talked about. If the line touches at only one point for all the way across, then we're happy, okay? But if our vertical line touches the graph at 2 or more points on the graph of this relation, then it can't be a function. Because remember, the inputs for the function are all of the x values, which can be visualized as tick marks on the x-axis. So this is the x-axis, so we put the tick marks here. These are the inputs. Here we can see there is an input, namely this x value, whatever it is, that's producing two outputs. So these could be, say, the points 3, 1 and 3, -1. So the input is 3, but there's two different outputs that are possible, namely 1 and -1. So this is why the vertical line test can help us to find out whether something is a function or not. So that's what we talked about last time. Are there any questions about what we talked about last time before we started on something new? All right, then the last thing I wanted to say before we actually start our notes is regarding domain and range of functions. So this is just something we have to get out of the way. The domain of a function is the set. Okay, so now we're using set again. So in other words, collection of all acceptable inputs. Okay, all acceptable inputs. So for example, f of x, why don't I give two examples actually? Gonna need an extra page. Here's example 1. Domain is specified. So we could have something like a table, a function which is represented via a table. So we could have x and f of x, and then here we've got like 1, 3, 7, and 2, 6, and 8. Okay, so here's a function. And the domain is the collection of inputs, which is namely 1, 3, and 7. So the domain is the set, so we do a squiggle, and then we put in the numbers which are possible inputs. Okay, so the number 9 is not in the domain of this function because they haven't told us what would happen if you plugged in 9. They're only defining this function for 3 possible inputs, so the domain is the collection, it's the bucket containing the 3 numbers that we can plug into the function. Okay, so that's the example of when the domain is specified. Sometimes the domain isn't specified. Example 2, domain not specified. So this is usually when they give us a function with a rule. They say f of x equals 1 over x. Okay, what this means is if I want to do f of 1, okay, all I do is I replace x in the denominator in the function rule by the number 1. Or if I wanted to do f of 2, then I would get 1/2, and so on and so forth, right? So I need to be a little bit careful here because they haven't told me what the domain of this function is. I have to return back to the definition of the domain, which says it's the set of all acceptable inputs, okay? And when I say acceptable, let me say actually what's not acceptable. What's not acceptable is division by 0, and even-powered roots of negative numbers. For reference, what I mean is like square root of -6. You can't do it. All right? Well, you can, but we're not going to do it in this class. Okay, so no division by 0 and no even-powered roots of negative numbers. We'll say a little bit more about the special case of logarithms later in the semester when we talk about logs. But those are the main two. No dividing by 0, no even-powered roots of negative numbers. So for this one, what I have to do is actually sort of intuit what is the collection of all numbers which I could plug into the function 1 over x, which will result in an acceptable input. Okay? So there's one big one which is not acceptable for me to plug in for x. What can I not put in for x?
0.
Can't plug in 0. So the domain is the set of all acceptable inputs. There's one which is unacceptable. So here's how I'm going to say the domain of this function. You could say it in 2 ways. 3 ways. First way is to say x is not 0. Okay, that's one way to say it. Another way to say it would be to say it's all real numbers except 0. So this is the way we say, so this symbol means all real numbers, and then we use a set minus to say we're taking away those elements which are in this set, which this set contains the element 0. So we're going to take 0 away from the collection of real numbers. So this is all the real numbers that there are, except for 0. Okay? The last way we could do it would be with intervals. We could say you can plug in numbers from negative infinity up to 0, but not including 0, and then union all the numbers from 0 to infinity. So these two things really mean the same thing, right? It's all the numbers that there are that are real, except for 0. Okay, because remember the open parenthesis means we don't include. Okay, so that's domain. Any questions about domains of functions? Okay, then the range of a function is simpler. Range of a function is the set of all possible outputs given an input in the domain. So let's see an example of a range. So first of all, let's say f of x is, say, the square root of x minus 2. Okay, f of x is the square root of x minus 2. Let's talk about the domain first. What sort of numbers can I plug in for x in this function? I think I heard it. Positive numbers, right? But I can't plug in negative numbers. Can I do square root of 0? What is the square root of 0 if we can do it?
0.
0. Why? Because if you take 0 times 0, you get 0. So that means that 0 squared is 0, or you could also say 0 is the square root of 0. So we can do domain should be all numbers bigger than or equal to 0. How about the range of this function? Well, now what I need to say is, well, look, let's suppose that I take a number, which is a positive number, and I plug it in here. What are the sort of outputs that I can get from this function? Yeah. What's your name again? Braden? Braden got it exactly right. It's negative 2 to infinity, because here's the deal. When we're talking about square root as a function, we're talking about the positive square root. Okay, so this is always a positive number. So this number is bigger than or equal to 0, and it can be as large as you want, right? You could take like square root of 1 billion to get like, I don't know, 100,000 or something like that. And then you could take like square root of 1 trillion to get a bigger number, okay? In order to get an output that is as large as you want, you just need to square that number and plug it in, right? So your output of this function can be as large as you want, but there is a lower bound, because the smallest that this number could be would be 0. And that would mean that the smallest output possible with the function would be negative 2. So the range is going to be negative 2 to infinity. And are we going to include or are we going to exclude? Why include? It's possible to have negative 2 as an output by plugging in 0, right? If I plug in 0, then I will get negative 2. So it is included in the set of possible outputs. So I'm going to put a bracket because it's included. Another way to visualize this would be to look at the graph of the square root function shifted down 2 units, which looks something like this, okay? So, set of all possible inputs, the domain, you can see, are all of these x values that you can plug into the function, right? What is the range? The range is the set of all possible outputs, all of the y values of points on the graph of this function. All right? So that's what I want to say about domain and range for now. We'll talk more about it later, but are there any questions on domain and range so far? Okay, then I want to launch into our warm-up problem for today. So I'd like for you to form groups of 2 or 3, okay? And we're going to work on warm-up problem A, B, and C together for about 5 minutes. I'm going to be walking around and helping. So if you get into a little bit of trouble, just raise your hand and I'll come over and help, okay? Does anyone not have a group partner? Okay, cool. Good.
It's not he's gonna speed up over time or something.
Slow down. Are you a math major?
No, I suck. Actually awful.
Did you do math or like science?
I just don't remember a bunch of numbers.
I can't imagine someone like I
Then the girls
Are we taking it like the witch? Like this is like literal factors are we taking in here? I feel like
until it reaches the peak, right?
That looks like a professional.
it's not a
It's a child. It's gonna go the other way and pull the child into the top. It's a small child. You can't have a actual problem. Just take it and go get the
No, I was gonna say like it's probably
I don't know about a 3-year-old walking up this. I was thinking That'd be so funny to watch though. A small child trying to raise a flag.
We had to do that in elementary school. Like every morning there'd be a different group of kids. And it was
Oh,
like
a
fifth
group
grade.
though. A group.
Yeah.
This is
I mean, like the security guards are leaving it for us. But we had to learn how to
This
raise
is
the
after the first
flag.
child.
Like really big ones.
Yeah, what if your friends like they want to do American
Is it windy? Is it windy?
Yeah, there's a tornado near the campus.
It's a thought. It's a thought. It's a start.
This looks pretty good. So this looks to me like, okay, the child's raising the flag, raising the flag, raising the flag, and then it gets to the top. And then what?
It's up there.
And then it's up there, just indefinitely?
I mean, until it hits. Oh wait, so we put it
Until-
back down.
Yeah,
So
probably
we
at
have
some
to
point.
go. I think a little
When the flag's gonna go down.
Yeah, but it has to be taken down. Yeah.
And then it'll go back.
Something like that.
So this is more like a thing. I didn't know we were talking about it going down. I thought it was like once it gets up there, the kids just gonna leave it.
Well, that's the thing. Okay, we got to be careful about the way these problems are worded, right? Because we have to interpret word problems in this class. And what I'm getting from the first sentence, it says, at summer camp, the child comes out every morning. That makes me think the time period we're talking about is like multiple days, right? Or even months, right? So I think our graph should probably try to.
Yeah. I don't know about just the morning. We're talking about just the morning. It's up there. It's up there. It's up there. No, this is like gonna give me. This ruined the entire page.
I hate trying to draw anything on a curvature like math.
Well, this class is gonna
No,
suck.
dude, like literally, look at you can see I erased this 70 times.
I think we could surmise that it's not just because up again.
All right, who all is finished with this exercise? Okay, does anyone want a little more time to work? Or should we discuss as a group? All right, let's discuss then. So, this is sort of the first example of a word problem that we have, and one of the crucial skills for this class is, of course, interpreting word problems. Taking a word problem and making it into a mathematical statement or mathematical question, answering that mathematical question, and then converting it back into language regarding the word problem. Okay, that's what we want to do. Okay, so it's this sort of 4-step or 3-step process, right? So the first thing to me that I saw a lot of people doing was a graph that looked something like this. Or some people drew a graph that looked a little bit more like this, which I'm also fine with, because maybe towards the end they slow the raising of the flag a little bit as it gets close to the top or something like that. These are both totally fine. But one thing that I feel like this fails to capture from the warm-up problem is the language in the first sentence, which says a child comes out every morning to raise a flag. That to me implies that it's going up and then it's staying there during the day, and then presumably in the evening it's going down, right? And then this process is happening over and over again. So the next thing that I saw was a graph that looked sort of like this, and I thought this was going in the right direction. Can anyone offer a criticism of this graph? Yep.
It's like never like fully down and stays like that. Like it goes down, but it doesn't. It just kind of like.
Okay, but if I extended it like that, would that answer that problem? Why else?
Because it's only accounting for like one day.
Okay, only one day. But let's say that I just repeat this for like several days over and over again. Is there anything else that could be criticized about this graph?
It's kind of saying the flag only stays up for the amount of time that it takes to like put it up.
Right. That's what I'm a little bit concerned about. Is that what you all were going to say as well? Okay, so the flag goes up. How long do we think it takes for the child to raise the flag? maybe 2 minutes.
How big is this child?
Okay, well, we're not going to talk about that because... All right, so then what happens? Then we have another period of time, which is like not very much longer than that. Okay, so the child puts the flag at the top of the pole. How about we say it like that? And then it's only up there for like 2 minutes. That's not very realistic, right? What's more realistic is it goes up for 2 minutes and then it stays up all day long, and then it takes like 2 minutes to take it down. So I would offer a graph that looks a little bit more like this. You could say, well, it goes up pretty quickly, and then it stays up for a very long time, and then it goes down quite quickly because it doesn't take very long to take down the flag. And then, again, it's going to be down for like all night, and then so on and so forth. So I like the blue graph a little bit better than the purple graph for that reason, since it doesn't take very long to put the flag up, right? And then to have all day, that's quite a long period of time as compared with the amount of time that it takes to put it down or take it up. Okay, so this is just a quick introduction to, well, number one, group work. So that's what I'm going to generally be doing during group work, is just kind of walk around, and I'll try to get to most people. I'll come to some people on different days, but if you want some individual attention, then just raise your hand during group work, okay? All right, so good. Any questions on warm-up problem A? Do we feel pretty okay about that? All right, then let's move on to functions. So, okay, I think what I wanted to put in here about functions was just what I have already said about functions, which is basically regarding the definition of a function, okay? So it's a relation which assigns to each input number a unique output. And I also wanted to put in there the anatomy of a function, okay? So we already kind of discussed this. I'm not going to rewrite it now. But we put in, okay, what is the dependent variable? What is the independent variable, okay? Spoiler alert, the independent variable is the input of the function, okay? So in goes with in, all right? So in this case, x is the independent variable, y is the dependent variable. In this one, t is the independent variable, and z is the dependent variable. We could even use another in word. We could say it's inside the function. Okay, so input is independent variable is inside of the function. Okay, so that's how I like to remember that. Okay, whoops. So, you know, regarding this, for our class, there's going to be an interpretation of both the input and the output. And one of our jobs is going to be to say, well, if we have a function, what is going to be the independent variable in terms of this word problem that we're working on? So say something like, I have the power to adjust the number of units I produce. The function then is going to tell me how much money I make, okay? So we want to be careful about what is the independent variable versus the dependent variable and interpreting these things, okay? So that's what I'm going to talk about next. So let's see. Okay, we want to give an example of a function encountered in everyday life. Okay, what is the input and what is the output? Okay, well, here's one that I can think of. Study time versus grade percentage earned. And then we can try to think of maybe what the graph of that function would look like. Right? What would the graph of that function look like? Well, maybe if you don't study at all, so this is time, and here's grade, and this is 100, and here's maybe, whoops, and here's maybe like, I don't know, 10 hours or something like that. So this is time studying for the quiz or something like that. Well, if you don't study at all, maybe you can hope to earn like a 30 or a 40 or something like that. So that's where our intercept will be. We're going to talk about that in a second. And then maybe the more you study, the more better grade you get, up to a certain point, right? And then maybe it levels off because at a certain point it's diminishing returns, right? So that could be an example of a function encountered in everyday life. Anyone have another one? What's another function we could have? L? Yeah, that's a really easy one to do. Amount of hours worked versus pay. In fact, this function is a special type of function, right? Because if you're an hourly worker, you get paid the same amount for each hour that you work, meaning that you earn $0 if you work 0 hours, but after that, it's a linear relationship, meaning that it is directly proportional, right? The pay is proportional to the hours worked, right? Okay, so that's a great example. Something that's not a function could be, I don't know, basically two things that are not related to one another, or something that violates the rule of inputs having different outputs. Okay, so here's an example. You could say weather type, or why don't we quantify it more like hours of sunshine versus day of the week. Well, the reason that this is not a function is because on Monday the 1st, you could get 12 hours of sunshine. And then on Monday the 8th, you could get only 3 hours of sunshine. Why is that a problem? Yeah, two different outputs for the same input. Okay, so this is, well, okay, if we're talking about day of the week, we're just referring to Monday. So Monday goes both to 12 hours and to 3 hours. So our function's not consistent, okay? Or if you wanted to graph it, it would fail the vertical line test, okay? All right, so that's an example of something that's not a function. Or just two quantities which aren't related to one another, like, I don't know, your grade in this class versus, I don't know, the amount of bed bugs in the entire Earth. They don't have anything to do with one another, right? Okay. Any questions on that? If not, then let's launch into the next group work. Okay, so we're going to work on problem 3 first. But if your group finishes 3, I want you to challenge yourself and do 4 and 5 together, okay? I think you can do probably all of them by now. And I'll be walking around to help once again. Oops. Sure, yeah. If you want, you can try to find, write this in function notation. Okay. Oh, I see what I put there. Yeah, just ignore my scribbling there about function notation. But yeah, if you want to write the function notation, you can. Sorry, what were you saying?
Oh, I was just asking.
Yeah, exactly. because right, the height of the tree, the deep end of the tree depends on rain. Right? You wouldn't say that how much rain will get. That depends on how much this tree is, right? That doesn't make sense. Trees are so many rain is not going to work. Yeah, just say it.
I have a question.
Yeah, what's up?
Yeah, so area,
Yeah, so the way we read that table, right, is x is on this function independent of x, right? So the independent variable is inside of the function. So if I see two on the inside, it means that we look for two on the part of the table with no height independent variable. Right.
oh, yes,
So, what is the input and what is the output? So, in other words, which thing depends on the other? So that the tree is going to grow a certain amount depending on how much rain we get, or is it that we're going to get a certain amount of rain depending on how much tree that's out here? Sure, yeah, right. So, I mean, in particular, what we want to be able to say, I mean, this is the correct function in the table, but what's implied by the function is since R is inside of the parentheses, then the quantity which R represents, which is the amount of rainfall, right, is going to be used in input. What makes you say that? Well, we have some numbers going to other numbers, right? That's all that are going to it, right? The relationship between some numbers and some others. We have some that are inputs and some that are outputs. The inputs are the ones on top, and the outputs are the ones on bottom, right? So, well, maybe what you're looking for is like a function rule, like x equals x squared. Is that what you're looking for? Yeah. So just because some functions have rules, right? Some of them don't. They just have a given set of inputs, a given set of outputs. When we write something like this, there is an implied set of inputs, all real numbers, which we obviously can't write all real numbers down. And then there's an implicit output, which is all numbers. In this case, the domain isn't all real numbers, it's just numbers. And if you wanted to make the graph of this function, it would look like a couple of dots. But it's still a function. As long as we obey one rule about functions. What was the one rule about it? You have to pass the vertical line test, which is another way of saying we cannot have more than, we cannot have the same input showing multiple outputs. But I think we're okay here because all of the inputs are different. 0, 2, 4, 8. Okay, how are we feeling? Do we need a little more time? Who needs a little bit more time to do number 5? Okay, so we're all done with 3, 4, and 5? Okay, then let's discuss. All right, so what do we think for 3? What is going to be the input in number 3?
Inches of rainfall.
Inches of rainfall, right? Okay, so what we're talking about here is what thing depends on the other. The dependent variable is how much the tree grows, right? Because that depends on how much rain we get, right? Whether or not this tree grows does not impact the weather system, right? So that's not going to be the dependent variable in this case. In this case, the input is R, the output is H, so we could write this as H equals F of R, something like that, if you want to use function notation. Okay, so the input always goes inside the parentheses, right? Inside the parentheses. All right, then for this table here, okay, the input is what's inside the parentheses, right? And the input is the independent variable, which we know is x. So when we see 2 on the inside of the parentheses, we're going to go to see where is there a 2 in the x row. That's here. And then I'm going to ask, what is the output? F of 2 is going to be whatever the output of the function is for that input. So it's 6 for this one. For f of 4, I think we get 3. For f of... Oh, and here we flip it up. Now we want to look for something where the output is 5. So I'm going to look in the output row for the number 5, and I'm going to find the input which gives me that output. Okay, so that's 0. And then the input which gives me an output of 2 would be 8. How about the next part? Is f a function? Is f a function? What do we think? Yes? Yes. So what's your name again? Owen's got it on the nose. It is a function. In fact, we can draw its graph, and its graph passes the vertical line test. What is on the graph? 0, 5, and then 2, 6, and then 3, 4 would be lower, and then... Oh, what am I doing? 3, 4. Sorry, 2, 6, and then 4, 3. So 4, 3 would be like here, and then 6, 0 would be here, and then 8, 2 would be up here, okay? So if I want to do a vertical line, am I ever going to touch more than 2 points if I move this thing left and right? No, I touch 0, 0, 0, I touch 1, 0, 0, 1, 0, 1, 1, 1. There's no point where I'm touching more than 1 point, so I can conclude by the vertical line test that this is a function. The other way is just to look, all of the inputs are different. There's no one input which is going to multiple outputs, okay? So yes, it is a function. And you can say so because vertical line test / no repeated inputs. Okay, how about the last part? Well, f of 4 is going to be the output of the function. So this is really a question about how do we get the graph of a function? Well, the graph of the function is the points x comma f of x, which means that the output of the function is going to be describing the height of our function. So we want to know, what is the height of our function when the x value is 4? So I'm going to go on the x-axis, I'm going to go until I see here is the x value of 4, and then this is the point 4 comma f of 4, where the height is the output of the function when we plug 4 into it, which in this case is what? 2. Okay, now I want to find the input which produces a height of 0. What's the input that I want?
2.
Yeah, 2 again. All right, so that's a bunch of stuff about functions and function notation and a little bit of word problem about inputs and outputs. Do we have any questions on any of that? All right, it doesn't seem like there are, so let's move on to something else and talk about intercepts. So, Here's what I want to say about intercepts. Intercepts are where the function graph touches one of the axes, okay? So you can imagine if we have a function which looks something like this, okay? There's a few intercepts, okay? Namely, here is one of them, okay? This point. And also this point here where it touches the y-axis. And also these two other points where we touch the x-axis, okay? Only we used to call them x-intercepts and y-intercepts, but sometimes we have functions where the input isn't x. We could have an input which is t, or we could have an input which is q, or any other letter. So what we've come to call them nowadays is horizontal intercepts and vertical intercepts, okay? A horizontal line goes left to right. So a horizontal intercept is going to be where does the function touch the horizontal axis, which is usually the x-axis, but it could be something else. All right? So that means that we took the input, we plugged it in, and the height was 0. That's what it means to touch the x-axis, right? Is the height of the function is 0 at that point. Okay, likewise for vertical intercepts, we know we're touching the vertical axis here, okay? So something like this. So this point here is a vertical intercept, okay? Because it's touching the vertical axis, the one that goes up and down. That's what vertical means, okay? So naturally, that's going to occur when the input is 0, because when the input is 0, we are on the vertical axis, okay? So plug 0 into the function, you get the y-intercept. Plug 0 in as the output of the function, you will find the x value, which will cause you to have x-intercepts, or horizontal intercepts. Any questions about the definition before we see examples? Okay, I have this marked as a group problem. Let's see, do we want to do group problem here? Yes, let's do group problem for number 8. Okay, so we got a word problem here. We want to do a little bit of interpretation, okay? A little bit of more interpretation. Coming up with a formula, and then we want to find the intercepts, okay? We want to find the x values such that f of x equals 0, and we want to find the output of f of 0 equals to something. Okay, so let's work on that in our groups, and I'll be floating around again. Actually, I'm going to get some water first.
What's gonna happen is the penalty is just how much less to 25 less
Okay, that's great. I will make a graph. Just make
I'm literally
Actually, no, another one.
I took pre-calc and I was like,
Yeah. I got like a 100% pre-calc, which is so easy.
No, my teacher was an actual, so I loved him as a teacher. I went and offered him.
That's actually
But like, as a teacher, he was just awful. It's terrible.
Anyone need some personal attention? So what we actually do is a relationship with our what we want is D is going to be equal to the output of our first two. So in where the is like not the output. The output should be the output. So we don't want to I like 6,000. But what's going to happen is the increase in T of 1 will get 66,000 plus 1,100 would be 607. Right. So we have that up as we go along. Negative 66,000. Each month, T goes up by 0.1. So we can subtract another. How y'all do okay? I did not. Okay? Talk me through it. Yeah. Okay. How's that? Which part are you on? Which part A? Okay. All right. So in this case, maybe we can go back to what we were talking about before, right? In terms of what's the input and the output, right? So does the month depend on how much I've paid, or does how much I've paid depend on how many months it's been? Okay, so I think I'm hearing the right ideas here, which is basically, look, the more months there are, the more I gotta pay, right? So that's telling me that however many months it's been is informing how much I have paid, right? So that means that time is going to pass whether or not you pay stuff, right? How much you pay is going to depend on how much time it's been, right? No, I think you said it right. Okay, so in this case, let's interpret f of 12 equals 52,800. So do we think 12 is describing the amount of money that you have left, or the amount of months? Probably the amount of months, right? So 12 is 0 for the amount of months. So what this says is, look, after 12 months, you finish the rest of the sentence. What's the right answer? Yeah, so you got a loan of 66,000 or whatever. After 12 months, you paid a certain amount, and now you owe. So that's the well, we'll work more on that later.
All right. Does anyone need a little more time to work? Okay, I'm not seeing any hands, so I'm going to talk through these together. So someone help me out with part A. So Kayla just finished college, and she has a lot of debt, and she wants to pay it down, right? So what is going to be the input of this function versus the output of this function? Someone tell me what is the input?
12.
Yes, 12. And 12 represents what? The number of months, right? So the input is the number of months, okay? One useful thing for these types of problems, look, time is independent of everything, okay? Look, whether it's rain or shine or you're alive or dead, time is going to pass, okay? There is nothing that is going to affect the passage of time, except maybe by coming to this class you make it go slower. But no, in reality, time passes and nothing affects it. So it's always the independent variable, okay? However, time does affect a lot of things, right? The amount of time you've been awake affects how tired you are. The amount of time your money's been in the bank affects how much interest you got, okay? So time's always the independent variable. So in this problem here, 12 is the independent variable, which is representing time. In the problem, we can find what are the units of the time. It says per month. That tells us that our input is going to be measured in months. So after 12 months, someone help me finish the sentence. Yeah, in front.
She still has $52,800 to pay off.
Yeah, $52,800 left to pay. Okay, good. How about f of 25? If I did f of 25, what would that represent? Yep.
I have a quick question.
Yeah.
Is the 52,800 output?
Sorry?
Is the 52,800 question, would that represent the output?
Yeah, that's the output, right? So the function's input is how many months it's been, and the output is how much left I still have to pay. So in this case, when the input is specifically 12, the amount left is 52,800. Yeah? Yeah, the answer for part B?
After 25 is the amount of months after 25 months after she began paying.
Yeah, so exactly. The f of 25 is amount of money left to pay after 25 months. Now, they don't tell us what that amount is, but this symbol represents that number, whatever it might be, okay? So you could say f of 12 is 52,800. When we put the equal sign here, what we're saying is, look, this is just another way of saying this, okay? 52,800 or f of 12. Whichever one you want to say is potato, potato. Okay, they mean the same thing. So in this case, they don't tell us how much it is, but this does represent how much money we still have left to pay. All right. So for C, let's talk through it together. I think the most useful thing to think about here is draw a picture of this, okay? T always goes on the horizontal axis. D is going to go on the, is it D? Yeah, D is D for debt, okay, is going to go on the vertical axis. So the first thing to think about is, well, how much debt do I have at the start? That's when T is equal to 0. I have 66,000, okay, 66K. And then what's going to happen to my picture here? As we go from left to right, what's going to happen to my debt? It's going to go down by the same amount every month. So there's a linear relationship here. So my debt is going to go down for a certain amount of time until I've paid it all. Okay? So it's a linear function. A linear function has exactly one y-intercept and one x-intercept. Okay, so that's what we're going to focus on next after we say what is the formula. So D is going to be the output of the function f of t, which we know should be a linear function. So it should be like mt plus b, where b is the y-intercept, which is 66,000. Okay, so that's the b value because that's the y-intercept. And how about the slope? What should the slope be? Yes?
Negative 1,100.
Yeah, negative 1,100. The reason that is because, look, for each month that we increase, the debt goes down by 1,100, okay? So the rise over the run, that's the slope. The rise will be negative 1,100, okay? Because we're going down. That's like a negative rise. And the run will be 1 month, okay? So we'll have negative 1,100 t. Oops. Oh, God. Negative 11. Okay, I better just erase the whole thing. Negative 1,100 t plus 66,000. Okay, so now if we want to know how much money is left after 25 months or whatever, we can just put 25 where we see t and do the math, and it would get us how much money we have left. All right, now let's do part C. So who can help me with finding the horizontal? Actually, why don't we do the vertical asymptote first? The vertical asymptote. How can I do that? How can I find the vertical asymptote of this function? Yeah, plug in 0 for t. So f of 0 is equal to negative 1,100 times 0 plus 66,000. What does that get us?
66,000.
Just 66,000. Okay? Now we got to be a little bit careful because when we talk about intercepts, what we're really talking about is a point, okay, on the graph. So the point is going to be whatever the input is and whatever the output is. We know what the input is. We know the input is 0. So the vertical asymptote is 0, 66,000. Whoops, too many zeros. How about the horizontal asymptote? How do I do that? How do I do the horizontal asymptotes? Or horizontal asymptote?
Plug in 0 for
Yeah, plug in 0 not as the input, but as the output. So I'm going to do 0 is equal to negative 1,100 t plus 66,000. Now what?
solve for t.
Solve for t, okay? So just use basic algebra. We move 1,100 t over to the other side. So we get 1,100 t is equal to 66,000. And then we divide both sides by 1,100. right? Which should give us 66. Okay, so we know that the horizontal asymptote is 66, 0, because after, with this input, the output will be 0. Hey, we're not done quite yet. Hang on. We got 4 minutes left of class, and still something left to do on this example, right? We should always get in the habit of asking ourselves when we're on an exam or a quiz or a homework problem, am I done? And you should be confident that you are done or are not done. So are we done with this problem?
No.
No, what did we still not do?
Interpreting.
We still did not interpret them, right? So let's do that, and then we can go, all right? How about the first one? The vertical asymptote is 0, 66,000. Someone tell me what that means in the context of the problem. Yeah, after 0 months, aka at the start of the loan period, she has $66,000 in debt. Okay, that's the vertical asymptote taken care of. How about the horizontal asymptote? You've already answered a lot today. Yeah, Aiden.
After 66 months, you got nothing.
After 66 months, she's debt-free. Okay? So, yeah, we love being debt-free. Good. So this is how we interpret these things. So, like I said, all of these problems, they start off with a word problem. Then what do we got to do? We had to translate the word problem into a mathematical function, and then do some stuff with that function, and then we had to do what? Translate back. Okay? So there's however many steps. We translate to math, we do the math, and then we translate back to English, okay? So that's the theme of this class. All right, have a good day. It should be 60. You're right, it should be 60. Thank you.